base 10 and 2. Let's first of all check to see how humans count. We're really used to counting of 10, primarily because we have 10 fingers. This is called decimal or denary. Let me show you a couple of numbers. Number 7 and the number 18. Why is this known as a 7? Because it's positioned in the column which represents units. This is the number 18. It's made up of 10 plus 8. The 1, the symbol 1 represents a 10 unit. Take another number, 278. 2 is positioned this time in the hundreds column. So 2 hundreds plus 7 tens, 270 plus 8 units, 8 times 1, 278. So it's known as base 10 because it's made up of the 10 symbols 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And depending on where you place these symbols, you represent different number. The first column is represented by the units, which are the ones. So those are 10 to the power of 0. The next column is 10 to the power of 1. And the last column here in this 3-column number is 10 to the power of 8. So you can continue this pattern to represent very, very large numbers in base 10. The symbols we have at our disposal are 0 to 9. This is base 10. Let's have a look to see how computers count using base 2, because we only have 2 symbols that we can use. This here is a decimal adder, and this was probably sold in its millions when the decimalization of the currency in Britain took place in 1971. Go and do a bit of research, go and read about the decimalization of UK currency. And this also is represented using units, tens, and the hundreds. So this is pounds, there's your pennies, and there's your new pennies. So we use this if you went to buy your shopping and you wanted to work out the new currency, because it was a new concept at the time, I imagine, in 1971. Okay, so the denary numbers weren't always written in base 10. This was not always the case. We never always used base 10. The ancient Babylonians used sexagesimal, decimal, I don't know how to pronounce that word, or base 60. The ancient Egyptians used base 12, and the Romans did not use numbered bases at all. They used letters, of course, C's and N's and X's and L's. Let's look at how computers count. Now, computers are made up of tiny, tiny switches known as transistors and capacitors, 2 of the most basic electronic components which are used to store a charge. So they are charged on or they have no charge. So they either contain voltage or a charge, or they do not contain voltage or a charge. So everything a computer stores or manipulates has to be reduced down to something, to a component or a whole combination of components which are either charged on or charged off. Here's a representation using a light bulb. When it's on, it's a 1. When it's off, it's a 0. These are the 2 symbols which are used by computers. Binary. So binary is represented using 1s and 0s. Computers will only recognize these 2 states, hence the term binary, bi, from the Latin word, means 2. Every switch then is called a bit. So binary and digit, you take the first two letters, the last letter, you form bit from these. So everything that the computer does has to use these switches, transistors, capacitors in the form of bits. How can we store numbers when using ordinals? These light bulbs are representing a switch. Put power through it, send some voltage in, it's a 0. Sorry, right? Put no charge in here and it's a 0. Put some charge into here, let's say you put 5 volts, 0 volts, 0 volts, no charge, it represents the number 0. Put some charge to it, it represents the number 1. Let's say you want to count higher than 1, you've got to add more bits. More bits means more transistors. It means the higher you want to count on a computer, you need to introduce more and more and more transistors. Okay, 2 transistors this time, or 2 capacitors which are going to hold a charge. Put them both off and they represent 0. Put 1 on and it's 2 to the power of 0. Anything to the power of 0, any number to the power of 0 is just 1. So if you switch this one on, the one on the extreme right hand side is representing the number 1. If you switch the one on the left hand side, in other words in the column, 2 to the power of 1, it represents 2. That's representing the number 2. Switch them both on, you've got the number 3 because 2 plus 1 is 3. So working from the right, the first bit represents 2 to the power of 0, the second bit represents 2 to the power of 1, and if we added another bit, that would represent 4, or 2 to the power of 2. Let's see how that looks like inside a column. Okay, take a look at this column. We've got 10 columns. Each column is represented by 2 to the power of a number. And if you turn them into base 10 numbers or denary values, as represented in this row here, this is the most important row, by the way, folks. We need to memorize these numbers. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and so on. These are the column representations in base 10. To convert a binary number then to its base 10 equivalent, we simply take the binary number, which is made up of only 2 symbols, 1s and 0s, and wherever the 1 is aligned, wherever the 1 gets aligned, we read off the base 10 number and add those bits together. Now, the highest number that can be represented on using these 10 columns here is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Switch them all on, add all the numbers together, and we'll end up with 1023. Now if you look at the 10th column, it's 2 to the power of 9. Yeah? So 1023, if we had another column here, it would be 1024. All of these bits set on is 1024, take away 1, 1023. What are the valves doing, or what's the switches doing? It's basically counting. You've got a count there happening. It's counting 1, 2, 3, 4, and so on. You can work that out. So to work out a binary value then in base 10, we can start with this table. Once we've got the table, I'll line up the digits, line up your binary numbers inside the correct locations, read off where the ones are, and add all the numbers together. So this binary number here is represented by 512 plus 128 plus 64 plus 32 plus 4 plus 2. Add those up and that gives you your answer of 742. Here's one for you to try. What's the value of this number? Again, first thing you need to do is draw up our column. Bring your column up. Once you have your column, once you have your table or row, position the numbers directly below and then add those numbers together. So I will just reproduce those on this. So 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. We don't need those ones. Notice how I started from the right hand side, and that's what I would recommend that you do as well. Don't start by going this way, because if you go from this way it's easier, because all you're doing is really multiplying the numbers by 2 each time. So this is the sum of this is 128 plus 32 plus 16 plus 2 plus 1. If you add these up, it's 128 plus 32, which is 151.60. 176 plus 3 is 179. Let's see how we can convert a decimal number now to binary using 12-bit storage. So 12-bit storage tells me I need 12 column headings. 12 column headings, my 12 base 10 values are also placed here. I take the 935 and ask myself, what's the highest value or highest column I am able to use? Well, I can't use a 2048, it's too large. 1024, too large. 512, yes, I can use a 512. So I take my 935, which I'm going to convert to binary, subtract 512, that leaves me with 423, which means I've got to use the remaining bits to represent 423. The next number, 256, is less than 423, therefore I need one of these 256s. So 423 minus 256 gives me 167. The remaining bits will be used to represent 167. We keep going from 167, we can have a 128, do the subtraction, leaves 39. We need a 32, we need a 4, a 2 and a 1. And then anything we didn't use is a 0. Binary number only uses zeros and ones. This then becomes my binary number. Easy. So 935 stored in 12-bit binary is this number. Sometimes you'll see this with a small 2 at the bottom. That's the subscript 2. Subscript means it's below the normal line of text. So it represents base 2. And the reason why we put a small number at the bottom is if you're working in number-based conversion, take this number for example and this number. This one is base 2, this one is base 10. We use the two symbols used in binary are also symbols that are used in base 10 and lots of other bases. So if you're working with bases, remember to stick your small subscript base number at the bottom. Let's do another one. This time we're going to convert the decimal number 1365 into 12-bit binary. So we look at the number 1365 and ask myself, 2048. Could I use a 2048? Nope, it's too large. I could use a 1024. I take 1365 and I subtract 1024 from it. I take one of these, so one of these are necessary. And you keep going again, so then we do 1365, take away 1024, and that leaves me with 341, and then 512, no, I can't use it, it's too large, but I could use a 256. Take a 256, do the subtraction. Whatever you're left, you've got to represent using the remaining numbers. You just keep going with this, and you'll eventually end up with a number like this. So it's 1, 0, 12-bit binary. So it's 12-bit binary. The first bit is going to be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And if you add up all the values which represent the switches, transistors which are on or a 1, then you would end up with a number which is 1365. Another method of converting base 10s into binary numbers is by dividing by 2 and then counting their remainders. Let me show you how that works. This method, of course, does get quite messy for large numbers, therefore it's not really recommended for very large numbers. Let's take a number 375. We want to convert this to its equivalent binary number. So we have 375 divided by 2 gives me 187, remainder 1. Take note of the remainder, write it down, then take the value of the number once it was divided by 2, move that on to the next line and do the same again. And repeat. And again. And again. Keep going. Saving all your remainders at the side. Keep going. Keep going. Until you can't do it anymore. And then we read these values. We read the remainders. But you've got to read them from the bottom up. What does that mean by that? You've got to read the numbers from the bottom up. So the 1 becomes the leftmost bit of our number. Read this way. Don't forget, you have to read this way. If you forget and read that way, you will have the wrong answer. 1, 0, 1, 1, 1, 0, 1, 1, 1, base 2. That's the binary. So this is known as the division method. So two methods I've shown you now for converting from a base 10 number. So you take the base 10 number, you can either use the columns method or you can use the division method. Now 375 was an odd number. Odd numbers will always have the rightmost bit set to 1. Why? Because every column has even numbers except for the last column, or the rightmost column. And that's one way of recognizing odd numbers in binary. If the number ends in 1, it's odd. If it ends in 0, it's even. Now we're going to work out another number, 211 in 8-bit storage. You try this one. Pause Welcome back. Is this what you got? Well, that's what you should have had. That's the answer here, using 8-bit binary. What's the highest integer number? Integers mean whole numbers, no decimal points. What's the largest or highest number we can fit into 8 bits? Well, 8 bits then, it just means we set all the bits to 1. And when we set all the bits to 1, we have 255. That is an odd number because the last bit is a 1. Another way to work out the largest number that would fit into 8 bits is 2 to the power of 8, take away 1. 2 to the power of 7, 8 bits. 2 to the power of 7 is 128. The next number here is going to be 256, which is a 2 to the power of 8. So 256 minus 1 gives me 255. So far, so good. What would happen if you tried to store a number larger than this using 8 bits? Well, we would result in something called an overflow. So number representation using bits, using specific amounts of bits, always has a maximum limit to the number that those number of bits can store. Very early programming was done using binary. There's a computer, you can go and Google search this computer, the Manchester Mark I, created in 1948. It's recognized as one of the first commercially produced computers. It's stored on magnetic drums, so it actually stored the operations for the processor. And the programming for this computer was all done using binary. Very tedious, very error prone. There's one of the manuscripts, and you can just about make out the ones and zeros that were used to program this. This has just come from some person's notes. This is quite old. The modern processor has billions of transistors, which means it can store very large numbers, of course, and those transistors will represent binary ons and offs, so switches. So it can hold data, it manipulates everything. Computers manipulate everything using number. So the largest number then you can store if you had a 32-bit computer. So let's say you had 32 bits, 32 buttons or switches or whatever that you can switch to on. You would have 2 to the power of 32 minus 1, a very large number. And 64-bit processors can store an even larger number. Here are some examples for you to try. Okay, convert these. Base 10s, convert to binary. Base 2s, convert to decimal. Pause. Welcome back. This is what you should have. If you didn't, go back, try again, keep practicing. Remember, you can make up random binary numbers and random decimal numbers, perform the conversion, and check your answers. You can either go online and find converters, or you can use the Windows calculator, switch it to programmer mode, type the number in. Depending on the base, you can choose the base and check your answers. Here's some common terms which are used to represent bits in a computer. If you had one binary digit, it's 1 bit. If you had 8 of those combined, it's known as 1 byte. If you took 1024 of those bytes, it becomes 1 kilobyte. And when we go on to look at hexadecimal, we have nibbles. A nibble is 4 bits. 1 byte is 8 bits, a nibble is 4 of them. which will be useful when we go on to look at hexadecimal. So just to summarize then, computers only recognize two states, the on and the off state. Switcher bit can't be between states, it's a 1 or a 0. Time delay between those states, in other words, the delay between the power going in or the power dissipating or being removed from that bit is negligible. In other words, you can ignore it. Anything that gets stored on a computer has to be held by combinations of ones and zeros. So text, audio, video, anything at all, color, anything that you do on a computer has to be able to be stored using ones and zeros. And I'll introduce you later on to how text gets stored, how color gets stored, how audio, and also how video is stored on a computer. So to store these numbers then, to store these simple integer numbers, computers use binary or base 2 format. And they can store values up to, depending on the number of bits that that computer has been created by the manufacturer. The maximum number you can store is 2 to the power of that number of bits minus 1. We can convert numbers from base 10 to binary or from binary to base 10 using either the columns method or the dividing method. And finally, if you were given some binary numbers, you can immediately identify by reading the last bit whether the number is odd or even. This here is an even number, in other words, divisible by 2 evenly with no remainders. These numbers are all odd numbers because the last bit is set to 1. Remember that, folks. You could be asked that in a question. That's us. Thank you.